resume our works, and I'm sure that people will soon start getting back in. And welcome back. Then the next invited speaker is Marino Gatto, professor of ecology at Milan Politecnico School, dear friend. And an ecologist with a great theoretical experience, actually, coming from the world of a IEEE world in tools-wise, etc. And the subject of the talk is discounting a multi-criteria optimization in ecology, evolution, and the management of renewable resources. So,
okay,
Marino,
thank
the floor is
you,
yours.
Andrea. Well, actually, this is the title I sent to you probably 1 month ago, and I was thinking about speaking about evolution, and then I finally decided to give up because it is too much. And also, Simon has been talking for quite extensively about evolution. So I think it's good for me to give up that. I would just give a hint at the very end of my talk. And what I'm going to say actually is not so new after all. I'm not talking about research I'm doing right now, but rather I'm talking about research I did in the past. It's more a kind of philosophical talk in a way. And I want to stress the fact that in many cases it would be good for environmental policies to use multi-criteria optimization. And that is something I mainly advocated in one of my papers, Pricing Biodiversity and Ecosystem Services, the never-ending story. So the outline. Well, first of all, I will talk about the management of renewable resources a little bit extensively. It will be a pedestrian illustration in a way, and I hope that the economists will forgive me. Probably they know about that already, but I think that the rest of the audience doesn't know very much about the management of renewable resources. And that will serve to point out the critical issues related to discounting, time uncertainty, the problem of extinction, the problem of substitutability, and that will bring me to discuss the concept of sustainability, and then finally, in a way, the focus of my talk, which is the problem of decision-making. What should you do to take a decision? Should you resort to benefit-cost analysis and pricing techniques, in particular to contingent valuation? Or should you resort to multi-objective analysis and the idea of the Pareto boundary, which is very much used by engineers? I am an engineer, actually, and if I have to describe myself, I'm both an engineer and an ecologist in a way. And finally, there will be just one slide about evolution, the spandrels of San Marco, but that is just to honor Venice in a way, since we stay at the Institute of Veneto in this beautiful city. So it's good to talk about the spandrels of San Marco. Now, so let me start with the problem of managing renewable resources. I had one of the greatest teachers that I met in my life is Colin W. Clark, and I had the pleasure to attend, I think the first time he gave a course on mathematical bioeconomics. Now, the simplest model is the one you see there, that you have a certain resource. That resource can grow with a certain growth rate, and you see an example there for the Finway. Of course, the growth rate is first increasing, then decreasing, then coming to zero at carrying capacity, where natality and mortality equilibrate in a way. And then you have an harvesting rate. And that harvesting rate depends on what? Well, it depends on the amount of capital and labor which is invested, which is usually summarized in one single measure, which is called effort. And you might measure that in number of hunters, number of operating vessels, etc. But it also depends on the level of the resource. That's rather simple. The more resource you have and the more you harvest, given a certain level of effort, and vice versa, given a certain level of the resource, you will harvest more if the effort is bigger. So it's, in general, it's an increasing function of both the effort E and the biomass X. And the simplest function you can imagine is a kind of local Terra function. It is just the product of effort, the human predation in a way, and the prey, the resource biomass X. So if there is no regulation, what will happen probably? It was Scott Gordon in 1954. He's now, I think, an emeritus professor of economics in Indiana, maybe, I'm not sure, who gave the answer to that question. And basically, the answer is very simply a prey-predator system where the evolution of the predator, which is the human effort, is governed by what? Well, the simplest thing you can do, you can think that the effort will increase if the total profit of the economic agents, for instance, the vessels, is positive, and it is decreasing if it is negative. Now, the cost is an opportunity cost, so it is not simply the cost, for instance, of fishing or hunting, but the cost of fishing or hunting plus the cost of not undertaking an alternative activity, okay? So that's a key point. So the idea is that the total profit is negative. There will be some economic agent that will be losing money, and therefore it will quit that activity. And on the other hand, since there is no regulation and that the total profit is positive, other economic agents will want to exploit that resource. So the idea is the one you see there. The evolution is similar to a Lotka-Volterra prey-predator model. You start from carrying capacity and an exploited resource, and you go to an equilibrium, which is called a bionomic equilibrium, because you have both the biological equilibrium, the x over dt equal to 0, and the economic, let's say, equilibrium, dE over dt equal to 0. Now, you can immediately notice that there are periods where the effort is bigger than the final effort, and periods where the biomass is smaller than the final biomass, but also from an economic viewpoint, that at that bionomic equilibrium, the net benefit is 0. The net benefit is dissipated. That's a key point. Here is an example, for instance, the northern fur seal, and that's the evolution of the exploitation. And you can notice that it takes about 20 years to go to that kind of equilibrium, and you have periods of overcapitalization and overexploitation. Now, actually, Scott Gordon did a static analysis of that. He was actually looking at the bionomic equilibrium in this way. You think that the the resource biomass is at equilibrium with the natural growth rate, which is equal to the harvest rate, and therefore, I don't go into the details, but basically, you can express the total profit as a function not of effort, but of the resource biomass at equilibrium. And what turns out is that total profit is just the product of what? Of the natural growth rate, which is equal to the harvest rate. So you multiply by the harvest rate, and the harvest rate is multiplied by the price of 1 unit biomass minus the cost. The problem is that the cost is not constant. Of course, it is increasing with decreasing biomass, because if the biomass is smaller, you have to invest more into finding that biomass, which is scarce. So what turns out is that the total profit is the blue curve you see there. So that total profit is 0 at the bionomic equilibrium, And of course, it is also zero at carrying capacity, because if you want to stay at the carrying capacity, you have to exert zero effort. Now, what you can notice that there is an intermediate level of the resource which is left, and an intermediate level of the effort which is kind of optimal, let's say, in terms of the net benefit, which is maximum. So, the moral, that at bionomic equilibrium, if there is no regulation, the net benefit is dissipated, which means that that activity does not have any added value for the society. You might obtain the same result by investing in another economic activity. Okay, Marta?
Just one question. If you don't have any threshold for the stock, then...
Okay, that's true. Okay, I'm, illustrating the simplest case. Then, of course, if you have threshold, then you might have a catastrophic transition and things like that. Okay. I do agree. But even with no threshold, which means that that resource biomass is well behaved in a way. Okay. Yet, you go to that bionomic equilibrium where the rent, the net benefit is dissipated. And therefore, the general result that you should introduce some regulation. But open access is bad, even from an economic viewpoint. No problem with ecologists, environmentalists, etc., but even from an economic viewpoint, that is bad. On the other hand, if you tune in a way the effort so that that effort is not very high, you can actually go to the optimal level of the resource biomass, and there the sustainable net benefit is maximized. Okay. However, there are two problems. That the sustainable economic benefit with no discounting, and also what do you do with a transient? Because initially you might not be at that optimal level. So, what do you do in that? Oh, I'm sorry. Well, you have to introduce discount rates, for instance. So introduce a present value. So the present value, you have the total profit I was talking about before, and then you multiply by an appropriate discount factor, and then you take, suppose that you are a regulating authority. That regulating authority will try to maximize that net benefit which is discounted. So you have an integral which is kind of similar to what part I was illustrating this morning. Now, let me give you my idea about discount rate. In general, you introduce discount rate because of two main reasons. One is uncertainty about future revenues. Better an egg today than a hen tomorrow, okay? And the other one is that you introduce a discount rate because there might be alternative investment. And therefore, you might think that investing money in that activity is not good. You might decide to invest that money or that effort, that labor, that capital into another activity. And again, you consider the most lucrative alternative activity, and that in a way that the discount rate, okay? And of course there is a lot of discussion about what the social discount rate should be. And there's been an illuminating paper by Parta on the Stern versus Nordhaus quarrel, let's say. What the optimal discount rate should be in climate change politics. Should it be 0%? Stern was advocating that. Or it should be 2%. If I well remember, that what Nordhaus was advocating. So there's a lot of talk about social discount rate. Now, But before discussing that, let me go into the solution of the problem of optimal regulation with discounting. Now, don't go into the technical details. It is kind of similar to what Pareto was illustrating, but it is simpler. So you want to maximize that functional mathematical term subject to the dynamics of the resource, and there is a certain level of the initial stock of the biomass, and then of course you cannot exert more than a certain effort. And if you look at the solution is like that. So there is an optimal level, X star, which depends on the discount rate, and the solution is a bang-bang solution, meaning that if initially the biomass is overexploited, the stock is overexploited, you should let the effort be zero. You should regulate, the effort is zero. If it is higher, then you can exert maximum effort and then go to what is called a singular arc. And the optimal level is the solution of that equation, this equation. Again, don't go into the mathematical detail. That equation is called the modified golden rule of capital accumulation because it is basically the same as the golden rule. And the problem is very similar to the problem, the Ramsey-Cass-Samuelson problem. And now you can understand why I wear a bow tie. It is not that I want to look like Samuelson, but when I was preparing my talk, I was trying to find a picture of Samuelson, and so I found that, and I said, oh, for a long time I have not been wearing a bow tie, so I might wear a bow tie. Okay. Now, actually, Samuelson was considering no linear cost, so the approach is not bang-bang. In fact, it's a very famous paper. It's called a catenary turnpike and the golden rule. Okay, but that's again technical. Now, if you try to understand this golden rule, it turns out that if you do a little bit of mathematics, it turns out that the difference with respect to the problem with no discount rate is simply that you add to the net benefit, to the sustainable net benefit, an extra cost. And that extra cost is, in a way, the cost of maintaining that capital. So delta, the discount rate, is actually the cost of capital. But how is that capital measured? That capital is measured in monetary terms. In fact, if you look at z of x, that function, z of x is the monetary value of the resource x, namely the cash that you would obtain if that biomass were harvested down to the bionomic equilibrium, or, as we will see in a moment, down to extinction, for instance. So you're very implicitly using the golden rule, you're giving a monetary value to that capital, which is actually a population of, say, baleen whales or the Amazon forest or whatever you want, okay? So basically the problem goes like that. You have a sustainable rent, which is that parabola-like function, and then you have a cost, which is the cost of maintaining that, of sustaining that capital, which is delta times z of x. And of course, the bigger delta and the higher the level of exploitation. And if you let delta grow very much, you go where? Well, you go to the bionomic equilibrium. So even if you regulate the resource, if you use very high discount rates, the regulation becomes closer and closer to the no regulation in a way. So, well, okay, that's kind of intuitive. So the discount rate is really the opportunity cost of one unit of capital. It's the cost of not disposing of the capital represented by the renewable resource. Now, I want to discuss explicitly that kind of cost, delta times the monetary evaluation of the resource, because that's the center, in a way, the focus of my talk. Now, first of all, the discount rate is really very important in terms of exploitation. So if you look at the calculation for the fin whale, the carrying capacity of the fin whale was about 400,000 individuals. The optimal population to be left would be about half the carrying capacity if the discount rate were 0. If you introduce a discount rate, say 5% per year or 10% per year, you go down and down. The current population estimate, by the way, now is about 84,000 individuals. Okay, so the discount rate is the most, well, I can say that. It's probably the most important factor in determining the level of exploitation of a natural population. Now, let me come back to the idea that the discount rate is conveying two concepts: uncertainty and the opportunity cost of capital, the alternative investment. Okay, now we have agreed upon the fact that we have to regulate this kind of economic activity. Renewable resources, because they are renewable, they must be regulated. If they must be regulated, and if there is an uncertainty, what should a regulating agency do? First of all, what should we optimize? Now, Matteo Marsili this morning was showing you that the objective function he was using was the average utility. But wait a minute. Now, if you consider uncertainty, look, for instance, at the graph on the right up. That's the return of sockeye salmon. So on the abscissa, you see the spawners, the number of spawners, and on the ordinate, you see the recruitment. And you can see that that recruitment is really a stochastic variable. There is a very high uncertainty. But the regulating agency has got data, so it can estimate the level of noise, the level of uncertainty, and then what should the regulating agency optimize? The present value is now a stochastic variable. The average? Why not the variance? And it is very well known that there is a trade-off between mean and variance. Now, my good friend Carl Wortley in 1975 was actually evaluating different policies for the sockeye salmon. You can employ different policies. For instance, constant effort policy, which means that you always harvest a certain percentage of the resource. Or you can introduce quotas, total allocated quotas. Or you can use a constant escapement strategy. Now, for all these strategies, you can compute the mean and the variance. And the basic idea that there are some strategies, like this one, which are certainly non-optimal, because they are dominated. There are policies which are better in terms of a higher mean and a lower variance. So the real problem and the real question is what to do when you are on the trade-off boundary, on the Pareto frontier in terms of the non-dominated solution. So my basic idea is that you have, even if you consider now the monetary value, for instance, or one single indicator, you don't have a multi-criteria optimization, which I will be advocating in a moment. In any case, even if you consider the mean and the variance, you really need to consider not just one performance indicator, one objective function, but at least two objective functions. But you might introduce a third objective function, which is, for instance, the probability of extinction.
So the uncertainty is in which parameter?
Well, uncertainty is, for instance, you can estimate uncertainty looking at, for instance, historically, you look at the so-called recruitment function. Recruitment as a function of the spawning stock. And the spawning stock, you can measure the spawning stock actually for the salmon, okay? And then you can say, well, the future recruitment will be that or that or that with different probabilities.
So,
and then you can compute. For instance, you can simulate. You can make a stochastic simulation in the future for the present value. So the present value is actually a random variable, and you can compute the average of the random variable and can compute the variance of the random variable. And you can understand, that I might be satisfied with a lower mean value provided that the variance is lower.
no, I understand all that, but I'm trying to relate it to your original model. And I was wondering whether it would make sense to make it small r.
Oh, yeah, that's possible. Yeah, that's possible. Yeah, sure. You can do that. You can do that. Okay. Or you can take, like in this case, a discrete time model where the recruitment in year t plus 4 is related to the spawning stock in year t. Okay. And then, for instance, you multiply it by noise. Okay.
You had originally a continuous model, so
Yeah, the original continuous model, which is not stochastic. Okay, so I was illustrating the non-stochastic version of the problem. Now, the way I see that is that in many cases you introduce a discount rate as a sort of way of including an uncertain future in a simple way. You are uncertain about the future. Okay. We can discuss about that. Individually, but if you have a regulating agency, I think it should behave rationally. And what?
Randomness is in the little r, it will be multiplicative noise. So it will be like...
I mean, for instance, in hydrology, if you have to manage a reservoir, you look back at what happened in the past, and you have to build a dam, or you have to decide what the release will be, what strategy you should use, minimum viable flow, etc., etc.
But also, what kind of noise would you think
and
of?
what kind of noise?
Is it Poisson, is it whatever it is?
Cetera,
because that transforms into a completely different...
Okay. So I mean,
mess,
I wouldn't simply increase the interest rate to take into account uncertainty. Okay, that's my main message. Okay, so even in this case, you need that. Now let me come to the second problem: the idea that delta is also an opportunity cost of capital. So it is conveying the idea that you might invest in another activity, or you might consider another capital. And let me give you the example of the decline of whaling. Now, if you look at the catch of whales, there are several whales. Of course, the blue whale is the biggest one, and then the second largest is the fin whale, etc., etc. And if you look at the decline of whaling, you can see that the blue whale had been peaking in the 1930s and then declining. Not because the effort was declining, but very simply because the number of blue whales was becoming smaller and smaller, and therefore it was more and more difficult to find a blue whale. And then they started catching the fin whale. Now, this is the Second World War.
You have to talk about it. Probably useful.
The Second World War, yeah, that's right. And of course, you should imagine to squeeze that window. And then the fin whale was declining, and then they started catching the sei whale, etc., etc., etc. Now that's an example of what the economists would call substitution. And in fact, that substitution is due to the rule which were implemented by the International Whaling Commission. So the International Whaling Commission was implementing total catch quotas, and these total catch quotas were in terms of blue whale units, where of course one blue whale is 1 unit, one fin whale is actually half a unit, etc., because they were smaller. And therefore, they were implementing a total catch quota in terms of blue whale unit without paying any attention to the fact that the blue whale actually was going to extinction, the fin whale was going to quasi-extinction, etc., etc. Until at a certain point, the resource biomass which was left was so low that it was very difficult to catch that biomass. And in fact, you can observe that the catch quota has been 15,000 blue whale units up to 1960, and then it has been decreasing, but it has been decreasing simply by trailing the actual catch. The actual catch, the total quota was 15,000, and they couldn't catch 15,000. They were catching 13,000. And therefore, the International Whaling Commission will say, well, for the next year, the total catch quota will be 13,000, etc., etc., etc. Now, the fact is that extinction can be economically optimal if the discount rate is sufficiently high. In fact, if you look at the golden rule and you assume some simplifying assumption, but basically the message is like that, provided that the growth rate, the natural growth rate of an animal population or a plant population is, under any condition, smaller than the discount rate, economically it is convenient, it is optimal to bring that resource to extinction, because that capital is not actually providing a sufficient return to the investment. But actually, that capital is not the property of someone, the property of humanity. Okay? So that brings us to the issue of sustainability and the definition of sustainability and the problem of how you actually define sustainability. That's the most famous definition of the Brundtland report. But then Bob Solow, and by the way, Bob Solow has been quoting Part extensively, came out with the idea of what sustainability should be according to his belief, let's say. Now, what you see there is sort of popularization of the weak sustainability which has been advocated by Bob Solow. So they say, well, development is sustainable if it does not consume the capital assets of a nation or the whole humanity, if you like. And you can think about manufactured capital, goods, building, infrastructure, the natural capital, the lean waste, the Amazon forest, etc. Human capital, the labor, cultural capital, beautiful Venice monuments, etc. And so the idea of weak sustainability is that, okay, we have sustainability provided that the sum of these capital is held constant, with the idea that there is a perfect substitution between capital types. While ecological economists say, well, no, there is some part of that capital which is not substitutable. And that is called strong sustainability. Now, I went through the original papers by Bob Solow, and okay, he says, well, after all, certain unique and irreplaceable assets should be preserved for their own sake. And he gives two examples, Yosemite and the Lincoln Memorial. Okay, these are very US-centered examples. Okay, and a few others. Okay, probably we don't. I mean, the Italians don't. We think about Venice, Florence, Rome, etc. Okay. And then you say, well, but most routine natural resources, now what is a routine natural resource? Are desirable for what they do, not for what they are. So, once a principle is accepted, we are in the everyday world of substitutions and trade-offs. Now, substitution is substituting the blue whale with the fin whale, etc., the sei whale, the minke whale, and bringing them to extinction. Now, I want to specify that in many cases he's talking about mineral resources, but mineral resources, okay, they're a very important example of resources, but they are not the unique resources, and in a way they are not the resources we, the ecologists, care about, in a way. So the idea of weak versus strong sustainability, that you have human-made capital, for instance, and natural capital, you sum them, but then you might have sustainability if part of the natural capital is destroyed, provided that the human-made capital is increasing, and provided that the sum of those two capitals is constant. Well, wait a minute. In order to make that sum, first, you must assume perfect substitution between capital types, and second, you must have a common scale for the different kind of capital. And that common scale is usually money. Okay, and I want to question about that. Now, before you saw that even if we consider money, in any case, you have a trade-off between mean and variance, for instance. So there has been a debate between two schools. Now, one school, not really led by Bob Costanza, but anyway, when you think about that school, you think about Bob Costanza. And the idea is that you try to value economically the ecosystem services and you give a monetary value. And the other school is that, for instance, of Rees, unfortunately, for all its theoretical attractiveness, ascribing money values to nature services is only a partial solution to the present dilemma, and if relied on exclusively, may actually be counterproductive. I must say that I agree with both Costanza and Rees. I agree with Costanza that the argument that we lose ourselves by economically pricing environment is silly. I do agree with that. We don't lose our souls by pricing the environment. But it's only a partial solution. It's only a partial solution. By the way, Costanza sent a new paper to me, well, and to many other people, I think 1 week ago, where he is re-evaluating the total value, the total monetary value of, let's say, natural resources. Now, let me compare these two approaches. So, the first approach, the pricing approach, you have to take a decision, and the instrument is the benefit cost analysis. There is one measurement unit, which is money, one goal, discounted social benefit, and then I would say average, because if you consider the variance, you don't have just one goal, but maybe at least two. And then you choose among alternatives. And the way you do the pricing, well, for instance, you can do that for sure. For example, you have air pollution, you calculate emissions, you can do that with mathematical models, spatial model. You calculate ground concentration, so you have concentration in different points of Italy or Europe. You can measure the damage in measurable units. There are now statistics, for instance, about morbidity or mortality given a certain amount of concentration of suspended matter, SO2, etc., etc. And therefore you have a dose response function, and then you can calculate the monetary damage. For instance, work days lost, and you give a value to work days lost, and you calculate total price. So several different methods for giving a price or for giving an indicator, because it is not only the price, it's not only the economists who have developed pricing approaches like hedonic pricing, traveling cost methods, etc., but even the ecologists have been developing their own indicator, the ecological footprint, or the exergy, or etc. But what I am questioning is the fact that you want to optimize just one single performance indicator. Now, let me give you an example of a pricing approach which is being advocating for evaluating the existence value. I mean, even in the economic school, they distinguish between utilitarian values, use value, and then they admit there is an existence value. No? And the way you can price that existence value is through contingent valuation. What is contingent valuation? Well, you have questionnaires, and then you ask people how much each one is willing to pay for a hypothetical welfare increase due to environmental amelioration or to accepting compensation for a deterioration. And the way you can see that, for instance, you have an unpriced environmental good, like water quality, for instance, oxygen concentration in the water. There is no price for oxygen concentration in water, okay? Then how can you price that? There is no market for that. Well, you ask people, how much are you willing to pay? And basically the idea is that of the utility function. You see there, on one axis, you have the unpriced environmental good, and on the other axis, you have consumption of a market price goods. For instance, beef or housing or whatever you want, and in that case, you have to pay. And the idea is that you're willing to pay something provided that your utility is left constant, okay? So you're initially at utility U0, and then you're willing to pay something, so to give up consumption of a priced good, provided that environmental quality increases by delta X. So that willingness to pay is in a way the price you will give to that environmental quality. Now, okay, suppose you do that, which is not so simple, but suppose you do that, then what you have to do is to obtain the demand curve for a public good, in the sense that Simon he was talking about public goods. Now, if you have a public good, for a given public good quantity, like water quality, you have the willingness to pay of consumer A, then the willingness to pay of consumer B, etc., and you have to sum all those willingnesses to pay. That's the total demand curve, which is different than the demand curve of a private good, which does the opposite. You don't sum the prices, you sum the quantities. But here, the use is not rival, it's not exclusive. So you have to sum the willingnesses to pay. Now, well, there are several problems with that approach. Now, first of all, the very definition of aesthetic value. You're willing to pay for saving the panda, which is, by the way, a very stupid animal, a low fertility, and it doesn't deserve to be saved. Okay. Are you willing to pay for having bacteria in the soil? I mean, if you ask people, well, of course, if there is good information and good education, if you educate people in order that they can understand that bacteria in the soil are very useful and they provide a service. And then, how many willingnesses to pay would you sum? Whales are mostly located in the Antarctica. There are no people in Antarctica. Would you ask Italians how much they are willing to pay for saving a blue whale? Also the Americans? What about French? So how large should be the reference group? Can you really think that the invisible hand of market, in a market for units of dissolved oxygen concentration, will really work? And then, of course, part of the natural capital is simply non-substitutable. The precise contribution of many species, we talk about biodiversity, is unknown. Ecological processes, in many cases, consist of interconnections. So, can you ask people about how much they are willing to pay for preserving an ecological process? And then there is free riding, okay? Actually, Simon was talking about that. That some people might not actually say, no, I will not pay anything for that, because they think that other people will pay for that. So what I advocate is that if you have to do decision making, my view is that you should use a multi-scale approach, where you have several attributes, you have several objectives. You don't measure that in one single unit. So you give up monetary evaluation, or even ecological evaluation, if you talk about ecological footprint or water footprint, okay? Fine, I mean, you should calculate water footprint or carbon footprint, ecological footprint, or monetary evaluation, but you cannot really believe that it is the single objective function to be maximized or minimized or optimized. And I think that is the right way for accounting for the existence of conflicting objectives. Now, what is strange to me that back in the 1960s and 70s, starting with the United States, they've been enforcing environmental impact assessment, and more recently, strategic environmental assessment, which was really a way for overcoming the problems which are created by cost-benefit analysis. More recently, we've been coming back to the idea that the free market is the one which would solve all the problems, and that we should give monetary value to everything, okay? Maybe I'm speaking a little bit too frankly, probably exaggerating. Now, let me give you a very simple, stupid example. You want to build a freeway and you want to minimize the cost. Of course, you want to minimize the landscape alteration. So you have several alternatives, and that's common for us, for the engineers. And okay, you calculate the landscape alteration, you can measure that, you can calculate the cost, you have different alternatives, for instance, these 7 alternatives, and clearly there are some alternatives which are non-dominating, the so-called Pareto boundary. So alternative 2 and 3 and 4 are dominated. They are certainly worse. Okay? And now each point is the result of a multidisciplinary study. You can ask say a road engineer to calculate the cost. You can go to a landscape ecologist and please give me an idea of the landscape alteration. But you don't ask the single citizen how much the citizen is willing to pay for a unit of a landscape alteration. That's unfeasible to me. So the Pareto boundary is a measure of the trade-off between two incommensurable objectives. Now, I'll give you, for instance, an example that is power system options in northern Kenya, where you have annual CO2 emissions and annual net present value. And in green, you see the Pareto boundary. And the Pareto boundary will immediately tell you something. For instance, that all these solutions are non-dominated, but clearly they have a much higher cost, and the benefit in terms of CO2 emissions is really minimal. Okay? But then you have the real trade-off. And my idea is that the trade-off is the subject of a political decision. That's a political decision. There is no rational way. Well, there are some methods, but there is no rational way to solve that conflict. You have to take into account all the different objective functions, and then you have to make a decision. Now, this figure, in a way, summarizes my idea. So you have the Pareto frontier. For instance, you have an environmental indicator. You would like to maximize that environmental indicator. You would like to maximize the monetary benefit. And then, of course, if you ask an environmentalist and the utility function for an environmentalist, the environmentalist would be willing to give up a unit of the environmental quality only if the monetary benefit was very, very high. So the utility function of what I have called an open-minded environmentalist is depicted in green. If you ask a developer, open-minded means that he or she will give some value also to the environment. But of course it will give more value to the monetary benefit. So the utility function would be the one which is dashed in blue. And then if you look at the Pareto frontier, their optimal solution would be D for the open-minded environmentalist and C for the open-minded developer, okay? And then someone has to take a decision. Well, suppose that it takes a decision like this one. Okay? It is clearly a decision which is a compromise between preserving the environment and preserving your wallet. Okay? Now, a posteriori, you can say, well, that 1 unit of the environmental indicator is priced so much, but that is only a posteriori. You draw the net benefit line, the tangent, this tangent here, and that will give you the monetary value of 1 unit of the environmental indicator, or, if you like, the environmental value of €1 or $1, okay? You can also see the things in an opposite way. But that's a posteriori. When you have to make a decision, that's an a priori decision. And also, the value, the monetary value you give depends on the context, depends on the decision, on the project you have to evaluate. That's my idea. So you cannot always use that price. So my personal conclusion, use pricing techniques and benefit cost analysis whenever this is reasonable. What do I mean? Whenever I can give a monetary value in a reasonable way for use value, for utilitarian value, use value, replacement costs, etc., etc. But in addition to that, perform a multi-objective analysis for all those aspects that are intangible: biodiversity, ecosystem, functional services. These cannot give a reasonable monetary value. And then make a decision choosing among non-dominated alternatives. Calculating the non-dominated alternatives is already an optimization, I think it's sufficient optimization. Spenders or Marco, last slide. So I was thinking about talking about optimization and evolution, but then Simon did that, fortunately. And also Simon explained one thing, discounting, okay, related to optimization and evolution. With reference to a specific problem, and that the problem of life history scheduling. Should I produce progeny when I'm rather young and the progeny, the male progeny is small, or should I wait? But if I wait, I might be dead, okay? And so I cannot produce my genes. Now, why the spender of San Marco? There is a very famous paper by Stephen Jay Gould and Nick Lewontin called The Spender of San Marco and the Panglossian Paradigm, a critique of the adaptationist problem. Well, now, for those of you who are not aware of the discussion among evolutionary scientists. Now, adaptation in many cases is seen like adaptation of a certain species, for instance, of genotype to the habitat or the environment, is seen like a problem of optimization. Now, what Gould and Lewontin were saying, well, that's a sort of Panglossian paradigm. You may remember that in Candide by Voltaire, Pangloss is the one who is advocating, we are in the best world of the whole possible world, and we have been created by God in the best possible way, because we function in an optimal way, etc., etc. So, Gould and Lewontin were saying, well, actually, you know, according to our viewpoint, things are like in San Marco, where you have the spandrels. I didn't know what a spandrel is. Actually, I don't. What's the Italian word for spandrel? Vela? No. No. Andrea, right. Now, the spandrel are these triangular sectors.
The different parts of the arches.
Okay, so, you know, they were saying, well, one might say, how beautiful these spandrels are, the mosaicists who are actually doing a very beautiful work, etc., etc., etc. And say, no, the spandrels have been done just because they have to support the dome. So constraints are more important than optimization. And they were mocking people. Some evolutionary biologists took that position as a sort of insulting position, etc., etc. And then, well, I stay with Parker and Maynard-Smith. You know, they kind of responded with several papers. I don't know whether this one is the most famous, the optimality theory in evolutionary biology. And, you know, the real story is that evolution, in a way, is partially optimizing. And so, of course, it is not always optimizing. But in some cases, you can look at some problems as a partial optimization, like the one cited by Simon. So, for instance, the problem of life history. Or, for instance, for a bird, what should a bird do? What is the foraging strategy? And it turns out that a bird has to especially a small bird, has to survive up to through the night. So that's a clear time horizon, one day, and it has to survive, and that provides sufficient food for that. But again, you can see that here there is a debate between two schools. One which is claiming that there is not one single objective function to be optimized. And the other one which is saying, well, okay, that is true, but we can look at a certain problem, and for that problem, optimizing one single objective function, which is, for instance, the amount of calories which are input in one day, or the fitness of a single genotype, the objective function. I think that the truth stays in between. Thanks for listening to me. Thank you.
Thank you so much, Marino, for this very interesting talk. In fact, very useful, especially for the, well, to bridge the two fields, actually. We have time for one brief question, because